Hello, ladies and gentlemen. Welcome back to the Monoxide Podcast. I'm your host, Harris, a.k.a. Monoxide, man of many automotive aspirations, and I am here with my co-host, Dan, Mr. Gunna Garage.
Yep.
And today we are... I think people will be offended if I call this Detroit. I think we're far enough away from the actual city, but we're close enough to Detroit out here. And today we are at Nostrum High Performance. And I want to preface this episode by saying that we may have a lot of technical talk in here, but I will do my best to kind of get down to the simpler terms because we learned a lot of cool stuff here today, particularly to do with injectors and stuff. And I think it was like, a 2-hour tour beforehand that we did here?
About that.
And we are here with Sam Barros, who is the director of R&D and research here, and man of many titles, let's put it that way, man of many hats. And then, of course, the owner of Power Labs, who, from my understanding, probably tunes the most Nissan GTRs on the planet, or definitely in the conversation.
I have been told that.
Yeah. Well, why don't we kick this episode off? You tell us a little bit about yourself, what Nostrum is, just kind of cliff notes, and then we can kind of just jump into the details after the fact.
Sure. So I came to the U.S. for my mechanical engineering degree. Always had a passion for cars. Somehow ended up working at a nuclear power plant while I was an engineering student. Got my first job in the special effects industry. So I lived in California for a few years, did high voltage special effects, and then I had an opportunity open up in the automotive field. Came here to Michigan and been here ever since. So I was the first employee for Nostrum Energy, which then became Nostrum High Performance. Nostrum High Performance is the aftermarket, so high flow rate, high performance fuel injector, fuel pump division of Nostrum. And with my leadership in R&D, we've grown from a operation in a university lab into what we are today, with, of course, very talented people like our VP Frank, our CEO Koshik, and all of the people that make everything here possible. So here today, we design and build what I think we can credibly say are the world's best high-performance direct injection fuel systems, as well as some port fuel injection fueling products.
I mean, the stuff that you showed us today was nothing short of remarkable. It was very, and again, the highlights after this episode will showcase some of the things that we discussed a little bit more in detail, some behind the scenes stuff. But there's a lot more to this than most people would think. And you guys, do you want to quickly define what Tier 1 means? Because that'll probably be something that comes up throughout the episode a handful of times. That's something that you guys classify yourselves with. Kind of explain what that means, and we can go from there.
Sure. So when it comes to vehicle manufacturers, you've got your OEMs, so your original equipment manufacturers. That's your GM, your Ford, your Nissan, Toyota. And then with the suppliers that make parts for these OEMs, you got your Tier 1 suppliers, which are the companies that make the parts that go on the vehicles that you buy. So, for example, you've got Bosch, Continental, Denso, Delphi. And then you have other companies that make things like service parts, replacement parts, so non-OEM parts. We are Tier 1, which is, I would say, not just unique, but potentially exclusive in the aftermarket industry, in that we make some parts that go in actual production vehicles. And we use the same engineering methods and processes to make our aftermarket parts. So,
within reason, right? So are you able to list off some of the customers you guys have? I know on your website, for example, you have AMS listed on the Nostrum website, which everybody knows they're one of the big dogs in the industry. You know, when it comes to quality of aftermarket support for various platforms and just quality. You don't have someone like that as a customer by accident. Is there any others that kind of fall into that high quality category that you're able to share?
AMS is certainly one of our favorite customers. They've been really good for us. Mm-hmm. We work with HKS as well, Livernois, Roush, Rentec, Weistech, Z1 Performance. I know I'm forgetting a bunch, but these are just ones
just off the cuff, right?
Hondata. Yeah.
By the way, I need to point out, one of these days somebody's gonna call me out. They'll probably think I work for AMS. I just love their shirts, dude. I got like 3 AMS shirts at home that I got from Texas 2K. They got by far some of the best merch. So
Their hats too. TX2K 21, I think it was. They
Okay.
had the big sombrero hats.
okay. Oh
And
yeah.
You remember that? Everyone was going around with them. I had to get one. Their merch is fantastic.
There's something to be said about good merch. So that I think probably like 1/3 of the episodes on this podcast have an AMS shirt. So it's not a coincidence they come up regularly.
Well, even the big shops that we've had on, we asked them what other shops they respect. AMS is always top of that list.
Always in that conversation.
Yeah,
Yep.
Absolutely.
So why is it that you guys do a lot of like direct injection? Like why not a bunch of port stuff? Why is it that this part of the market stuck out to you guys?
So the reason why we got into aftermarket fuel systems, it wasn't something that we had planned on doing. It came about by accident. So what happened was we were doing some research with water injection in our research laboratory up at Michigan Tech University. And we started out by doing port water injection, and we were finding that a lot of the water was ending up in the crevice volume between the piston and the cylinder, and then it was going down into the oil sump and essentially turning the oil into a chocolate milkshake. So we needed a better way to handle the water injection. We realized that if we're able to direct inject the water, we could wait until some compression had already happened and the air was hotter. So then when we injected the water, it was going into a very hot environment and it would start evaporating faster. No one made a water injector, so we designed one and we filed patents for it, and then we set up the manufacturing capability to make a direct water injector, which is very expensive. So now we've got a direct water injector and absolutely no market for it, and we just spent a bunch of money on that. And I thought to myself, well, no one makes an aftermarket high flow rate direct injector. And there are a lot of cars on the market. I remember at that time the Corvette LT2 was really starting to pick up in the aftermarket.
And what time period is this again for most people?
Ooh, God, when did we start doing? When did the C8 Corvette came out? Right around then?
2020?
Yeah,
2020?
Yeah.
That sounds about right.
Yeah.
So we decided that we were going to use our manufacturing capabilities to make water injectors to design a gasoline high flow rate injector. Lingenfelter was our first customer, and we started making exclusive injectors for them. It sold very well. Customers are happy. It was the first time that you were able to make big power DI. They made 1,500 wheel horsepower direct injection only on an LT4, which we're really proud of. Oh, C7 Corvette, not C8. I got my timeline wrong. Yeah,
Okay.
it was a C7.
So then this would be probably about over 10 years ago now, probably,
Yeah,
roughly. About
8 years ago, I
8, 9,
think.
okay, that makes more sense. So why does this matter to the customer, right? Because that's mostly what this podcast is catering to, is the general customer, like people like me and Dan, like, let's say we might buy a C7 Corvette or a C8 Corvette. How does this translate into like real world gains? Like whether that's drivability or power or maybe both? Explain or touch on that a little bit.
I think that's a really good question, because ultimately, I think if we have done a good job in designing a fuel system, you should not know or care that your car has a fuel system. Mm-hmm. What I mean by that is when you know a car is modified. It's when you can hear the fuel pump from outside the car, right? Or you've got a car that just idles like crap because it's got 2,000 cc injectors. These are visible evidence that you have an aftermarket fuel system. That's the worst thing in the world. You just spent a bunch of money to make your car worse. We never want that. So we want whatever we make to be as transparent as possible. Mm-hmm. The fuel system delivers additional fuel to make power when you want it, but it's not affecting anything else in drivability.
So you're talking about car running like crap. You mentioned 2,000 cc injectors. I feel like this is a good spot to ask. So in a lot of applications of car builds, right, you overshoot your horsepower goal. We talk about this all the time on the podcast. If you have a car, your goal is 1,200, make sure you're building it for 1,500 horsepower or something. Give yourself a buffer there, right? Can you explain to me why I wouldn't want to do that in an injector sense? I should be upgrading my injectors as I go along, not shooting for a high injector and then with a low horsepower application?
Sure. So I think there are some areas when you're building a car where it pays to overbuild, right? For example, if you're building an engine, you don't want connecting rods that are rated for 1,000 foot-pounds in an engine that's making 1,000 foot-pounds. I know mathematically it checks out, like, hey, it said it should be good for it, but the moment you get a knock event, overboost, anything, that connecting rod is going to fold over, come out the side of the block. But there are other areas where overbuilding makes the car markedly worse. A friend and I were talking about the 10 worst mods you can possibly do to a car, right? The modifications that will make you not want to drive your car. I would say maybe number 1 on the list, a clutch that's way too heavy. We've all driven cars that have clutches that are
It's
just...
the worst.
It's the worst.
Especially in drift cars, or like I had a friend that had a S13, had like, I think it was like a stage 3 clutch or whatever the heck. However, it was the worst car on the planet to drive.
Yeah.
So that's number 1.
Oh, like it's heavy, it chatters, right? So that's one where if you were not very knowledgeable about cars and you're building a car and let's say you're building it to make 1,000 horsepower and you've got all these clutches out there and you don't know anything about clutches and you're like, I'm going to get the 1,500 horsepower race clutch because it's the best. And then you go drive it and it is just the worst thing you could have put in your car. So that's one. Another really good example, before I directly answer your question, would be camshafts. It's the same thing. Everyone knows that if you get a bigger cam, bigger here meaning more lift, more duration, you can make more power. So what people who are not yet very knowledgeable about modifying cars do is they say, well, I'm already going to tear the engine apart. I'm going to put some cams in it. Let me get the best cam. And then they get like the race cam that has the biggest lift and the biggest overlap and the biggest duration. And then the car doesn't idle properly. It doesn't want a cold start. It surges. It bucks at low speeds. It sucks to drive.
Before we get too far into the show, I wanted to take a moment to talk about Raise a Hood. If your daily driver is having issues, aka your beater you got off Craigslist, Raise a Hood's telemechanics and AI tools can help you diagnose and solve the issues you may be dealing with for a fraction of the cost. All you have to do is add your car to the Raise a Hood garage to get started. You can provide the AI tool, also known as Gus, with the specifics of the issues you're having, and it'll help you narrow down what the culprit is. It's a great way to bounce ideas off of to figure out what actually might be the problem. You could then select from a variety of solutions to explore the cost and difficulty of doing the repair yourself versus taking it to a shop. If your car doesn't have detailed solutions yet, that's totally fine. Just go ahead and add your car to the garage for free, and that'll let the Raise a Hood team know what to focus on as they continue to develop and grow. If you want to try out Gus or chat with a telemechanic, go to raiseahood.com and add your car to the garage to get started. Use code MONOXIDE-FREE for a 1-month free subscription, or Monoxide20 to save 20% on a 30-minute call with a telemechanic. Let's get back to the show.
It's the same thing for the fuel system. At some point, if you get a fuel injector that's big enough, it will no longer be able to idle at lambda 1, meaning we will have to force the injector to inject additional fuel at idle just so you can get the injector operating in a region where it's stable. So what that means is fuel injectors are linear in that if you double the amount of time that it's open for, it will inject double the amount of fuel. But as you shorten the amount of fuel that you're injecting, there comes a time when they become non-linear. And for most cars, that happens when they're trying to idle. And if you get an injector that's so big that you're idling in the non-linear region, you get very poor idle characteristics. I always tell people you should get the fuel injector that's big enough to meet your highest power goals on E85 if you're running E85, because that's 30% additional consumption compared to gasoline, but no more. Going too big in fuel injector is one of those things that will make the car much harder to tune and much less enjoyable to drive.
Okay.
So that's one thing that we kind of haven't really touched on this podcast, and this is kind of a segue, but when it comes to E85, discuss just how, when it comes to designing your fuel injectors and when you're choosing fuel injectors for a vehicle, you have to take into account that E85 is going to be, you're going to be dumping way more in there. Why is that?
So the reason for that is if you look at the ethanol molecule, it has an OH group. So there's some oxygen in there. And I know some people think that it's like bringing oxygen into the combustion chamber, but that's actually not true. It's just partially oxidized. But what that does is it means that for you to burn the same energy worth, let me reword that. What that means is ethanol has less energy per volume. So for you to make the same amount of power with ethanol as you do with gasoline, you need about 40% more fuel. It doesn't mean ethanol doesn't make a lot more power. It does. It's a much higher octane fuel. It has higher latent heat of vaporization, which means that it cools down the air charge more, so you get lower temperatures. It's denser, you can run more time. It's a wonderful fuel. But the chemical characteristics of it are such that you need 40% more for a stoichiometric air-fuel ratio. So, blanket statement, if you're running E100, you need 40% more fuel. This is wonderful for a fuel systems company like us, because it means that if you want to run your car on E85, you're going to run out of fuel right off the bat. Very few factory vehicles have enough headroom capacity to run full E85. And then when you crank up the boost to make more power, you can very easily run out of fuel system capacity. So once you have enough fuel system to run full E85, you can reap all of the benefits, but it is one of the biggest reasons to upgrade your fuel system. And I will add something else. You haven't asked about it, but it's something I think it's really important. Ethanol gets a bad reputation for being hard on fuel systems. And in particular, there's this phenomenon with E85 or running cars on E85 called slime or sludge. And what happens is a lot of times if you're running a car on E85, it creates this sticky film that coats the inlet sock at the in-tank pump, and it plugs up the inlet. Or sometimes the sticky film will plug up the direct injection fuel pump, and it clogs up your fuel system. And what's causing that is not the E85. E85, everything in E85 is fully soluble in E85. And everything in gasoline is fully soluble in gasoline. But fuels are not one single chemical compound. In gasoline, there are detergents, there are oxidation inhibitors, there are a lot of additives that go in that. And ethanol also has an additive package that does things like inhibit corrosion and so forth. Well, it turns out that the additive package of E85 precipitates out when you put gasoline in it. It's easy to see that if you're doing the ethanol, the E85 test, where you get a little test tube and you add water to it and you shake it and then like the gasoline portion comes out. That's how you test for E85 without an electronic tester. So what's precipitating out is everything that doesn't dissolve in water. So the problem with the E85 is not running E85, but rather running those intermediate blends. You get the sludge when you run your car on E30 or E40 or E50. That's the point at which you've got just enough gasoline in there and just enough ethanol to pull out some of the compounds. And these are polymeric compounds, meaning that they're like plastics.
Right, yeah.
And they create that film. So if you want to run E85, run E85, full E85, no blending, no go to the 85 pump, 3 gallons of this, go to the gasoline pump, 5 gallons of that, get a calculator, just do it right. And then you don't run into these issues.
So are you saying something like E30, E40, E50 or whatever, that's kind of like a Band-Aid for something then?
It's the worst thing you can do for your fuel system. It works.
Okay, noted.
Yeah, it works in that you're getting the octane benefits of the 85.
Right.
And you're making power. I'm not saying it doesn't work to make power, but in terms of what it's doing for the fuel itself and the likelihood of you creating issues, it's the worst blend.
What kind of issues are you like? What kind of issues will be the result of that then?
It's usually the sludge that I was talking about.
Clogs
The
up
sticky
everything.
film clogging things up.
But there's like a whole chain of things that could probably happen after that too, then, right?
Usually you clog up your inlet and you lose fuel pressure at high load. Hopefully it drops fast enough that the car just misfires, cuts out. Maybe it leans out instead of cutting out, and then you could potentially melt a piston. But
These are all easy things to fix, I'm
yeah, yeah.
sure. This is a cheap fix.
Ask me how I know. Is there a blend? So when you test it, right? Would this be, because sometimes you can test it and it's only 40% or 50% right from the pump. Would that still be okay because it's still in its blended form from the lubrication company that they get their fuel from?
Exactly.
Okay.
Yes. And
so it's the mixing of the two from the pumps is where the problem lies.
that's what it is.
Okay.
Yes. And again, it's not like every time you mix it, it will do that. For example, we were talking to the guys at Cobb, and they were saying that there were certain regions in the country where this seemed to happen much more than in other regions. And it may have something to do with what additive packages are being put in on these fuels. So I'm not saying that this is going to happen if you blend it, but I'm saying if it's going to happen, it's because you're running those blends.
Okay.
You mentioned specific parts of the country.
It seems to be Arizona, California, New Mexico, Texas, which incidentally, great states, but Arizona, New Mexico, California, Colorado, they're 91 only states, and it is like Chinese gas levels of knock-prone garbage fuel. It's incredible. If you've ever been on the Cobb website and you're looking at their Access Sport off-the-shelf maps, they have specific maps for those parts of the country. So
That's hilarious.
you can tune your car on 91, or you tune it on like California, Arizona, New Mexico 91. It's so much worse. They had to spend the time retuning the cars just for that fuel. So maybe it's that specific fuel blend and whatever the hell they're putting in it that makes it so bad that maybe comes out a solution when you add the 85. But I'm postulating at this point.
Mm-hmm.
It is funny how even though it has that number on the pump for what your octane rating is, that makes a difference. So when I tuned my orange car, my tuner said I cannot use 91 non-ethanol. He says I can have 91, but it's got to have that at least 10% ethanol in it. Otherwise, I get a little bit of knock. So even though the octane rating is at 91, they want a little bit of alcohol in the fuel in order for me to run that. So it's 93, 91 with at least 10% is what I have to run in that one.
Interesting.
Yeah.
So then, how do you look at that from a tuner perspective then, aside from the Nostrum part? Now, because you also, again, you're a tuner, you tune a monstrous amount of cars. What's kind of your response to that then?
So when I'm tuning a car, I always start out with a base map that's based on the worst quality fuel I think the customer is likely to run.
Okay.
Which is always that. It's I call it the California map. I've had GTRs in California where I started with the 91 map, took 2 degrees of timing out, and the car is still knocked. So I ended
Wow.
up with a timing map that's conservative enough to not knock in California. I just recently tuned a car in Egypt, and on the California map, it was knocking 7 degrees. So I guess Egypt has worse gasoline than California.
That's a crazy consideration you have to think about then. So like if you were to, not necessarily you, let's say me and Dan, whatever, we owned GTRs in different parts of the country. So I'm, back home in Minnesota. I don't know what the gas is like there. And then he has one in California. Would that theoretically mean the one in California has just less power, generally
Absolutely.
speaking?
100%.
Wow, okay.
Yeah, and no way around it.
Well, actually, you can kind of touch on this. I've heard this before, but maybe you can kind of elaborate on it. It's not necessarily the fuel itself that makes more power, is it? Is it just because its properties allow you to make more power, or how does that work?
That's a good question. So the answer used to be that it makes no difference. So what I mean by that is if you take a car from 15 years ago and you put C16, 116 octane on it, it will not make any more power. Now, one of the myths that gets perpetuated on the internet is that it will make less power because race fuel burns slower. So that is incorrect. The burn rate or the flame propagation velocity of a fuel has absolutely nothing to do with the octane rating. There are high octane fuels that burn a little bit faster than pump gas, and there are high octane fuels that burn a little bit slower, and the burn rate does not have a dramatic impact on anything relating to engine operation. So generally speaking, if you have an older car, 15 years or older, and you add high octane fuel to it, you will not net any benefits unless you tune for it. Recently, this stopped being true. So something happened about 15 years ago or so, in that a lot of OEMs started incorporating a strategy that is sometimes called dynamic advance. And what this strategy is a lot of newer cars, the GTR being an example, Porsche being my favorite example. Porsche is very, very aggressive with dynamic advance. They are continuously adding ignition timing until knock onset. So if you have a Porsche 911 and you're running 91 or you're running 93 or you're running 96 octane, the ECM is always adding more and more timing until it finds knock in one cylinder, and then it will stop and it will keep adding more timing in every cylinder until it finds knock onset. And it's able to do that because the engine is strong enough to survive a very weak knock event because you're just barely at the knock threshold. And the ECM is fast enough to see the knock the moment it happens and then pull back. Whereas ECMs from 30 years ago would knock many times before they were able to detect and do something about it. With dynamic advance, we're finding that some cars, again 911 being one that I'm more familiar with, they will keep making more power well past pump gas octane levels. So if you put 100 octane on a 911 turbo, you will actually make a little bit more power. Nothing remotely comparable to going in and tuning the car to run more boost and making all the other changes, but enough to make an argument that it does benefit from higher octane.
So something like a stock like 911 turbo, you'd probably pick up like something like what, 20, 30 horse, something like that?
20-ish, something like that.
Does it hurt a car that doesn't have dynamic advance? So I'm going to bring my orange car back into play here again. Whipple Mass Air car, tuned for 91 or 93. Let's say I pull up to a pump and a station's close to a racetrack. They have 110. I put 110 in my car. It maybe doesn't have dynamic advance, but am I hurting anything by going over octane?
110 will hurt it.
Okay.
Why? Because the highest octane fuel that exists, that is gasoline based and is unleaded, that I know of, is VP 109. So what that means is if you find a fuel that has more than 109 octane, it has lead. And the problem with lead is it will clog up your cats. And if you don't have cats, it will clog up your oxygen sensors.
Okay.
I have seen a car run through a whole tank of 110 and lose all 402 sensors before it was out of fuel.
Really?
So, and on a car like this, you could be looking at $600 to $800 worth of oxygen sensors. So because it's leaded, that would be a problem. Now, if
it wasn't leaded, let's pretend it's 100 or something.
You're buying yourself margin of safety, which is always a good thing. I always tell my customers, if you're racing your car, just put race gas in it, or run E85, but run it out of a drum. Run like R85, racing ethanol, because more octane is always a good thing. If the car gets too hot, if you're doing like a long pull up a hill, if anything goes wrong, having the additional octane can save the engine. So it's never a bad thing unless you're running leaded fuel.
Okay.
Here's a little sidetrack. You definitely didn't see this one coming. Have you, given your position, right, with tuning and then, of course, the profession that you're in here, have you ever tested, like, between the different ethanol brands? So, for example, like you got one ethanol and then I'm blanking on the other names, but
VP's another one that does a product.
Right.
Yeah.
Have you ever done any testing between any of the brands, see if there's any differences?
I have. So
And anything that won't get you in trouble?
it's a little disappointing. So it was my personal GTR.
Okay.
I was fuel pump limited. I had what did I have? I had dual Walbro 525s with a voltage booster, and just really, really marginal fuel system. And I was able to run E65 on the car.
Mm-hmm.
And I pushed it to the absolute limit of what I could do on that fuel. And the car made just under 1150 wheel. So then I put dual brushless pumps, and I went from E65 to E98. And I was thinking, I've got so much more octane here, surely it will make a difference. And the car did not pick up any power whatsoever. So in that particular example, I was not knock limited on E65. So there was no ignition timing to add. I was out of turbo, so I couldn't add any more boost. So really the question was, is there something particular about E98 that makes more power than E65? And the answer was no, there isn't. But in a situation where you're knock limited, on a GTR, on E85, it will happen around 45 to 50 plus pounds of boost. So once you're running 50 pounds of boost and you're making 1,500 wheel horsepower from one of these cars, they can knock on E85. At that point, having an R85, which is ethanol blended with race gas, will raise the knock threshold, let you run more timing, and let you make more power. But these are very extreme cases, and I would make the argument that if you're running such an aggressive calibration that you're knocking on pump E85, you probably have no business turning it up even higher past that just because you've got racing ethanol.
So that's another great, that's answers another question for me, kind of. So I was told by my tuner, again, we tuned this car, and every time I tested it every time as I was sending him logs, and every time it was over 80%. But he told me I was good for anything over 60%. So even though he's tuning, he's looking at logs at 80%, I'm assuming he's either put a buffer in there that I can put 60, or there's not that much of a difference between 60 and 80 that it even makes a difference. Is that kind of what you're saying?
That's exactly it.
Okay.
So most of the benefits from ethanol blends happen by E50.
Okay.
Again, going back to what I said, on extreme cases where you're just running extraordinary amounts of boost or very high compression ratio engines, there is a benefit to the higher blends, but most of the ethanol is in there by E50. The way I tune cars is by E70, I'm making full power.
Okay.
I don't like to go as far down as E50 because I don't know what gasoline is in there, right? It could be E50 where it's 50% 85, like 85 octane. I just don't know. So I prefer to play it safe because the ethanol sensor is only measuring ethanol. It doesn't know what your gasoline fraction is.
Well, if you're commercially tuning cars, right, you're not going to be in business very long if you're blowing cars up left and right. So I'm assuming there's always got to be you're factoring in a buffer there. Unless I'm assuming that if you had like a high race application, you're working with somebody who does it professionally. They know the risks. You're taking everything to the ragged edge at that point.
Yeah, and the risk benefit is very skewed in this business because let's take this car for example, right? So it's a factory engine, factory transmission car with turbos.
Mm-hmm.
It has enough turbos to make about 1,000 wheel, and it probably will make 1,000 wheel on the factory engine at least once, maybe. But if I do it, and let's say the car gets out of the dyno making 1,000 wheel factory engine, right? Some newbie tuners will be like, hey, new world record, highest horsepower factory engine GTR. Most people that know the car won't really care. If you want to make 1,000 horsepower, you're going to build the engine. You're going to make however much power you want. And then the customer takes the car out, starts street racing it, does a couple back-to-back pulls, puts some heat in there, engine blows up, $20,000 repair bill. Easy. I don't think you can put a rod out the side of the block in one of these and get it back on the road for less than about $15,000. And the customer is going to be very upset, and justifiably so, because my ego is the reason the car blew up if I did that. And then he goes online And then the moment word gets out that like Sam Barros blew up my car, that's a big chunk of my business that's gone.
Oh, I'm so cutting that, by the way. Sam Barros blew up my car, and then that's the highlight.
Don't do that. Yeah, that definitely.
I'm just messing.
But it's really important to remember that that extra 10% power that you make from a car doesn't really feel any different, right?
Mm-hmm.
Like if you're making 500 wheel, or you're making 550 wheel, or you're making 800 wheel horsepower, 880, it feels the same. Maybe with a draggy, under controlled conditions, you do some back-to-back runs, you're going to see a small difference. But it doesn't feel any different. But the risk, as you go higher and higher in power, as you approach the limit, it rises exponentially, right? So smart tuning, good tuning, is not what is the most power I can possibly get out of this. It is what is a sensible performance level to provide to the customer where the car is fast, but it's also reliable, and there is some margin of safety in there because his wife might put 91 on the car, or maybe 87, or maybe it ends up with some water in the tank and the ethanol content reads high, or it could be a very hot day. A lot of things can happen, and it's really important to build a buffer in there where, of course, we can't forecast everything and protect against all conditions, but we can certainly make it less likely for the car to break. And I think that's the biggest part of the job.
Yeah, you break one once and then tell me how you feel about that, that number. I had a friend of mine that had a 2013 GT500, and it made 994 on the dyno, and he was so upset that he couldn't say he had 1,000 wheel because he was off by, which in the grand scheme of things, like you would just tell people you have 1,000 wheel car, right? But he was so upset. By the way, about 2 months later, that car blew up.
Mm-hmm.
So it's, and now he doesn't have that car anymore. So which would you rather have, 6 more horsepower or a car still?
It's very true. And the other thing to remember is that even if money is not an issue, right? Like, even if you're wealthy enough that you can just put another engine in there, it doesn't happen right away. Car's going to be down for months. And usually it breaks down in the middle of the driving season. We're in the Midwest. We've got a pretty short driving season here. Peak driving months are, you got June to about September. And if the car breaks in the beginning of the summer, that's a big chunk of that year that you can't drive it. So there are many reasons to be conservative when you're tuning, and not too many to try and get everything out of the car that you can, unless it's a race car. And then if it's a race car, of course, it's a whole different conversation.
Right. They're switching those engines out between events at sometimes.
Right.
Between runs.
Yeah.
And then running on the
extreme.
ragged edge is what makes the difference between
Right.
winning and losing, right? So I've got a financial motivation now to push it more. But on the street car, you just have to find a good balance where it's fast, but also it's still reliable.
So let's talk ultimate street car, right? Which is stock cars. How are we able to see more and more of these cars, right? Where you have the SF90, the Revuelto, the new ZR1, which is the best out of all those.
Arguable, but that's fine.
Just being inflammatory. But anyways, how is it that you're able to get 1,000 horsepower from factory now? I mean, especially with how strict EPA stuff is. And we will have a more intense discussion on a future episode as well with someone coming up. But it's harder and harder to squeeze more power out of cars reliably, outside looking in. How are you able to get 1,000 horsepower out of a stock Corvette now?
Yeah, I think the real question, because obviously we've been doing 1,000 horsepower engines since engines were created, right? 1920s, maybe.
Yeah.
How do you do 1,000 horsepower in an emissions compliant vehicle under a warranty? That's incredible. And then kudos to the entire GM team for that beast of a car that is the ZR1. And of course, you've got the Bugatti Chiron making 1,500 horsepower, and Koenigsegg has got 1,500 horsepower plus monsters. So the fact that OEMs are able to do that today and do it in a way that passes emissions is absolutely incredible. And I think the engineering to make engines strong enough to survive that much power has existed for a very, very long time. So there's no revolution in that aspect. The engineering to do that on pump gas, on the other hand, and do it in a way that passes emissions and is reliable is really the magic. It's a lot of different factors, and it gets into a lot of very technical things. But broadly speaking, I think we could narrow this down into two primary factors. One being the combustion system. So the combustion system is where OEMs spend all of their money when they're developing a new engine. It is said that a clean sheet engine design, start to finish with emission certification, costs about $1 billion.
Oh my
And
God.
most of the cost is in the combustion system. When what the combustion system is how the air comes into the engine, how the fuel is injected and mixed with the air, and then how the exhaust exits and is treated. And inside the combustion chamber, the primary design factor for the combustion system is in the charge mixing. So how do we mix the air with the fuel, ignite it, and burn it? And the reason why this is so important is on pump gas, which is really the only thing that's relevant to OEMs, right? On pump gas, we are limited in how much power we can make per cylinder by knock. There is a point at which if you keep adding more boost and you keep advancing ignition timing, you're going to knock. And at that point, you will either break the engine or the ECM will react and pull timing, and then you're going to lose power. And knock is a time-dependent event. So once the spark plug fires, the air-fuel mixture starts to burn, and the clock starts to tick. Everything that hasn't burned yet is getting hotter and hotter because it's being exposed to radiant heat from the mixture that is burning. And at some point, the mixture that hasn't burned yet can auto-ignite from how hot it has become. And the longer it takes for the mixture to burn, the more time it has to get hot enough to auto-ignite. So modern combustion system design prioritizes very fast burn chambers. And the driver for how quickly the mixture burns is how fast it's moving. So it's the charge motion inside the combustion chamber. What GM did that is genius is they took a page out of racing and they moved the fuel injector from the intake port into the exhaust port. This is called the cross-flow injection. So you've got the air coming in from one side, you got the fuel coming in from the other side, and the fuel spray reinforces the charge motion of the intake charge and leads to a very fast-moving air-fuel mixture that burns very quickly. Because it burns very quickly, it doesn't have a lot of time to knock, so they can run a much more aggressive boost timing curve and so forth, make a lot more power. We were talking yesterday also about the giant turbochargers, way, way larger than what you would theoretically need to make that much power. And the main driver for that is trying to get as little exhaust back pressure as possible. Because with exhaust gas back pressure, you get residuals, which is hot exhaust gas in the cylinder. So you're starting off with a hotter charge. And again, if it's a hotter charge, it's going to get hotter once it starts burning, and then you're more likely to knock. The other factor, of course, is the engine controls. Very fast computers that are now able to run the engine right on the ragged edge of self-destruction, but know not to go too far and are able to detect and pull back right as things start getting out of hand. I'll finish this with an interesting anecdote. You know, the 2JZ, the legendary Toyota Supra engine.
It's all right. I'm kidding.
I like the way it sounds. And I mean, like by today's standards, right? It's pretty dated. But what do you think made it so strong? Why do you think it is that you can crank the power up so high on those engines?
Well, I remember watching a video on it. I can't remember who it was. I think it might have been Driven for Answers or whatever. It was talking about just the structural integrity of the block itself, wasn't it?
But it costs money to make a strong engine, right?
Mm-hmm.
And if you're designing a car for 300 horsepower, why would you want the engine to survive 800? You could cut a lot of cost by making it weaker. And the reason they did that is that they had no way of adequately addressing knock. So they knew that there were going to be certain operating conditions where the engine would knock, and knock detection and knock mitigation was very primitive back then. So what Toyota did is they just built it to survive that. And now, if you put modern engine management and you're running high quality fuel and you keep it from knocking, you can make a ton of power. So today, every new car can stay right on the edge of knocking but not actually go there. And with dynamic advance, it can walk right up to the edge. So you're really making as much power as it possibly can, and you're able to keep it there and keep it alive because of how capable modern engine management is.
Now, are they sometimes using diesel components in a gas engine? Sometimes in those situations, even some, I think by accident. I don't know if a B58 is what I'm thinking of or whatever it is, but because technically a diesel engine almost runs off knock, right? There's no spark that happens. It's the compression of the fuel and air and the heat from the compression that actually fires it and shoots it off, because you only have a glow plug to warm up the cylinder beforehand. So is that and they can go 300, 500,000 miles pretty easy on a diesel engine because they have stouter components for that reason.
Yeah, so a couple things with diesel. They are much stronger, and the reason they're stronger, of course, is horsepower is a function of torque and RPM. Diesels have long burn durations, so you can't run them at very high RPM. You essentially outrun the combustion of your fuel if you try to run a diesel at 8,000 RPM.
Yeah, I think my truck redlines at 5,000.
Right.
Yep.
So to make power, if they can't rev high, they need to make torque. Torque comes from cylinder pressure, so everything has to be beefy in order to survive those cylinder pressures. In gasoline engines, because we run them at much higher RPM, diesel components will be too heavy. You would just end up with these inertial loads from heavy pistons, heavy rods, pulling the engine apart. Another thing, too, is it's a common misconception that diesel engines run by knocking. There are certain operating conditions, namely cold start, where the fuel injector fires and you get some air-fuel mixture in the chamber, and then during compression it ignites, and that is the definition of a knock event. But under normal operating conditions, diesels are what's known as diffusion burn, and what that means is the compression happens, you get a lot of heat into the air charge, and then the fuel injector fires, and as the fuel injector fires, the mixture is burning. So it's actually burning as it's injecting, and your burn duration is more or less the injection duration. So if you look at the pressure trace for a diesel engine, it's not one sharp spike where everything burned instantaneously post-compression. It's actually a longer burn that's related to the injection event. Okay. Otherwise, they would never be able to survive full power. And if you're getting a knock event at maximum charge density, it will blow the diesel apart.
Okay. Which we've all seen those videos of them blowing apart on dynos.
Tractor pulls. Oh
Yeah.
my God.
That's
That's my
spectacular.
guilty pleasure. Tractor pull videos. There's this one where literally the engine blows out of the tractor and then he drives over it. I must have seen it 1,000 times. Have you ever seen that one?
I don't know if I have. Maybe
I'm gonna have to
maybe.
show it to you later. It is legendary.
Yeah. You definitely keep up to date with exciting things like that. I've seen some of your posts or comments. I'm like, this is amazing. Let's talk a little bit about Nostrum again, because we kind of got away from that. I wanted to talk a little bit about the OEM side of things with the ZR1, which I think it's nothing short of a modern marvel of engineering. I mean,
Agreed.
We'll see the reliability when it comes out, but yeah, I agree. It's pretty great on paper.
What was going on with your transmission earlier?
It leaks, but it's still working.
Yeah, GT500 things.
Yeah.
Okay, so let's kind of go through the process here, right? Because you showed us a number of ways that you guys make injectors here and such, and keep them to such a high standard. Before we get into the nitty-gritty details, why is it that you guys are special with what you do, right? What makes you a unique offering to the marketplace, and to who?
The thing that makes us unique in the market is that we're a tier 1 that sells to the aftermarket. So We are designing fuel injectors and fuel pumps to the same standards, using the same processes, the same certification as what you would find in the factory components in your vehicle. But we're doing this for a high performance, high flow rate application in the aftermarket. Specifically, what that means is we have in-house capabilities for things like patternation, dynamic testing, arc flash imaging, high-speed imaging, manufacturing capabilities that you typically wouldn't find in any aftermarket company.
And so why does that matter to like a regular Joe like me or Dan, or more so even like a high-tier performance shop that just kicks out a bunch of aftermarket products?
Well, just in general, walking through your facility, you guys have more testing equipment than you do manufacturing equipment. Would that be
true.
right?
Absolutely.
Good
Yeah.
point.
Right.
Well, because the money in aftermarket is in getting cars through the door, right? So if I own a performance shop, or if I'm a calibrator and I'm doing this for a living, my revenue is how many cars I can get done in a month. And if a customer comes to me with some mystery injectors, I'm not going to name any names, but they come with one single piece of data. It will say flow rate is 1700 cc's per minute at 100 bar, and that's it, right? So I'm a calibrator. I get the injectors in there. I change the flow rate. I start the car, and it just doesn't idle, because there's all this data for short pulse duration performance that I don't have. And obviously this injector is aftermarket, or it's been modified. The behavior is not the same as the OEM injector, but I'm running all the OEM tables. So the car has all these drivability quirks. And now I have to spend hours and hours and hours just guessing and checking and fudging data to get the car to run right. As a shop, that time is very difficult to bill to the customer. If I get some garbage mystery injectors and it takes me 8 hours to finish a car, do I charge the customer 4 times as much? He's not going to be okay with that, right? So the reason why the test equipment is so important for us is we believe in equipping our customers, customer in this case being the shops and the calibrators, for success. So we provide all the data and a calibration guide such that you can plug in everything, start the car, it starts fine, it idles fine, it runs fine, and then you can go back to just doing the calibration work that you were going to do in the first place, without having to fudge anything to make the fuel system work.
Basically saving calibrators, losing that word. Basically saving calibrators a ton of time then.
Time is money.
Yeah.
So I showed you a sheet earlier from another company that was probably smaller for port injection on a car that I had on it. And when I was working with the tuner, they said, hey, we only work with this brand or this brand. I bought that brand, put them in the car, but I didn't have anything in the box as far as a sheet of paper like I did with the other brand. But in that case, because they're such a large supplier and they're working with all of these tuners, they would already have that data on file, right? So you guys have a lot of relationships that you have with the tuning companies themselves as you're selling this stuff. They don't, each customer, as they buy that injector information, they don't need that information because you already have it to the people that should be tuning their cars. Is that correct?
We still provide it, and
Okay.
All of our dealers, they have a web portal that they can log into, and they can download the data, and they can download the tuning guides as well, so it's always available.
Okay.
So kind of talk about, injectors aren't exactly simple, right? Outside looking at, like you guys were showing us earlier, it's like, oh, well, you look at this, these two look very similar, but then you show us these different charts and maps and whatever, and they perform very differently. How can injectors differ from one another? Like, what are some things that you're looking for, and for what application? What are some things to consider? And maybe this doesn't even apply to the average tuner or whatever, but this is who's looking for that data, and what exactly are they going to be looking for, I guess?
So I'll start off with an anecdote, and it's not related to what we do here, but it's something that I learned several years ago that really stuck with me.
We'll get back to Sam in a moment, but I just wanted you to think about how you found this show. Someone likely shared it or sent it to you, and as a result, you're here. So if you can think of another car enthusiast who would enjoy this episode, send it their way, and let's get back to the show.
So the modern diesel fuel injector is the highest precision engineered component of any industry in the world. So what that means is the manufacturing tolerances for a modern diesel fuel injector are tighter than anything you would find in aerospace or Swiss watchmaking or anything else. The pintle to pintle guide clearances are in the order of 2 microns, and the stroke, the distance between the pintle and the back of the pintle where it's actuated from, is in the order of 1 micron.
So explain what that is, by the way. A pintle.
So human hair is about 200 microns.
Okay.
Oh, the pintle is it's a needle that is sealing against the seat. So it's essentially the moving component that does the valving for the injector, that controls whether there's flow or no flow.
Gotcha. Okay.
So the reason why I'm mentioning this is we don't put a lot of thought into fuel injectors. It's just another component. But fuel injector technology is where the highest precision in a vehicle takes place. And it has to, because in order to meet emissions, we need perfect fuel metering for perfect air-fuel ratio control. If you're not able to accurately control your air-fuel ratio, your catalytic converter doesn't work, and then you fail emissions. So there's a big incentive there. And a lot of engineering goes into making these parts as precise as they are. Mechanically speaking, they're not very complex, right? So you've got a solenoid, which is an electromagnet. The electromagnet is acting on an armature, which is a moving part, a piece of iron that the electromagnet can pull to lift the pintle or the valve, if you will, off its seat. And the opening of a fuel injector consists of just electrical power being applied to an electromagnet, which makes a part move to open it. It's the precision with which that is done that matters so much. And to have high precision, you need careful measurements, and you need the metrology and all of the equipment that goes into being able to verify that things are being made to that degree of precision. Most aftermarket companies are focused on increasing flow rate without perhaps as much thought to the rest of the equation. And you get these injectors that will deliver fuel, so you're going to make power, but there are trade-offs in drivability and trade-offs in idle quality and cold start that you can see a difference with when you go to those injectors.
Well, we're also talking that this event happens anywhere from 1,200 to 8,000 times a minute, right? So that's for a tens of thousands of miles on an engine.
Yeah.
That has to be pretty reliable, I would assume.
That is true, absolutely.
So what are those other considerations, right, beyond flow rate? What does that look like?
Sure, yeah. So
And why does I mean, I guess if you're talking to, like, again, somebody that's tuning GTIs, not as big of a consideration, I imagine. But if you're in a performance aspect, whether you're racing cars and you're trying to get every single ounce of whatever aspect, what are those considerations looking like?
Absolutely. So if we go back to what we're talking about just a moment ago with the magic of OEM high horsepower and how a lot of it comes down to the combustion system, the fuel spray is a critical component of your combustion system, meaning where are the fuel jets going, how are they targeted, how many are there, how well is the fuel spray breaking up. And that fuel spray is a function of where the holes are drilled in the injector and how they're drilled. I think some time ago, one of our competitors figured out that they could just put an extra hole in an OEM fuel injector and increase flow rate by 1/5. And it does work. You put an extra hole in the injector, you end up with more fuel coming out. But without a correctly drilled stepped hole, the way the OEM does it, you just end up with this slug of fuel that comes in, doesn't break up properly, doesn't atomize, impinges on the piston top, you get liquid fuel on your ring lands, there's liquid fuel going down to the oil. a lot of disadvantages. So correct fuel atomization, proper spray targeting, proper spray shape are very important. Another one is some genius online every once in a while figures out that you can get a DI injector from one car and put it in another. I'm not going to name any of the ones I'm aware of because it's just such a poor idea, but in general, a lot of DI injectors look the same, and a lot of times you're able to get an injector from one car and put it in another car, and sometimes that injector can flow more. But the problem is, unless the combustion system is identical, you're going to end up with a spray pattern that's completely unsuitable for your engine. Then you end up with smoke and soot and washing the bore walls with fuel and just a lot of disadvantages.
When you say combustion system, so what are some things to consider within a combustion system? I guess, and maybe you mentioned this earlier in the episode, but a reminder, what defines a combustion system then?
So combustion system is inside the combustion chamber, how the air is coming in, what the charge motion looks like, whether the airflow is tumbling or swirling and how it's tumbling, how the fuel spray comes in and interacts with the air charge, and then how the spent air fuel mixture is purged from the chamber.
And that's typically affected by, let's say, like, piston shape probably?
Yes.
Okay.
So if you put a flat top piston in an engine that was designed with a dish piston, you are impacting the combustion system. In particular, that little dish in the middle of the piston is not there because manufacturers want to increase surface area to drive up surface area heat losses and lose efficiency. It's a big trade-off thermodynamically. It's there for a very specific reason, and the specific reason is that little bowl is there to guide the fuel injection event towards the spark plug for improved cold start. Once you do away with that, you get an engine that doesn't cold start and doesn't cold idle very well. Similarly, the fuel spray is designed for that particular injector location in that particular engine with that particular piston shape. If you put an injector that has a completely different spray pattern, it doesn't work anymore, and you see trade-offs in drivability and smoke out of the exhaust and cold start quality and so forth.
These are all normal Volkswagen things, by the way.
Well, it's like that across all engines. If you watch the different generations and iterations of motors as they come along, a lot of times it's the heads get redesigned, the intake plenums. I mean, if you just look at the generations of the Coyote, every time there's a tweak to the intake plenum. Now the Gen 3, are we on 4 now?
4, yeah.
Has twin throttle body intakes. Like a lot of the air intake systems change throughout generations.
That's true. Yeah. They're doing that to drive up volumetric efficiency. So if you look at the Corvette Z06, it has a variable runner. So they're able to change the effective runner length on the intake manifold, and then that changes where you make peak torque. So you're essentially able to optimize it for 2 different power bands.
Yeah, when you get down to even in a 4.6 that Ford had since like the mid-90s and a 5.0 Coyote, there's still a modular engine. That once you get down to the short block, they're not that far apart. I would assume the same thing in the LS world. Once you're down to the short block, it's an LS.
Yeah.
So one of the things you kind of touched on, like I think it was last night, you're kind of talking about how OEMs take different approaches, right? So how Mercedes does one thing and then the new ZR1 does another. So for example, you're putting the injector on the exhaust side or whatever it is. And then Mercedes has a different style where they're trying to get, the tumble more quicker? Kind of touch on that as well, because that was a super interesting kind of comparison you made last night.
Yeah, so this is something I learned watching a presentation from Mercedes-AMG at the International Powertrain Symposium in Cologne a couple years ago. And they were talking about the highest specific power gasoline engine. It was I think it's M188. I could be mistaken, but it's a CLA 45 AMG. So 2-liter turbocharged 4-cylinder, 400 horsepower from 91 octane. So 200 horsepower per liter, emissions compliant with a warranty. And what they were talking about was that the key enabling technology for being able to do that was creating the fastest combustion system, the fastest burn chamber that they had ever done. So they designed a step on the intake port and the intake valve that causes the air to tumble as it comes into the cylinder, and it tumbles at a very high velocity such that when the spark plug fires and that flame kernel forms, that the vortex of swirling air carries the flame into the entire cylinder very rapidly and burns the air fuel mixture fast enough that it doesn't have time to become to transition into knock. And one of the things they said that I thought was really interesting is that they were able to make it burn even faster, but the limitation became NVH. They were getting these burn events that were so fast that the engine would ring under normal combustion as though it was knocking. So they were approaching some of the not technical limitations, but practical limitations of engine design, in that, well, we can get more power from it, but the customer is not going to like the fact that their Mercedes-Benz sounds like an old diesel.
Yeah, you basically mentioned that it was like getting too loud or whatever it was.
Because it was burning so fast, right?
Yeah.
So you get this really rapid pressure rise, and it sounds like a pinging.
So then that kind of leaves a little bit on the table for the future then, as well as we all know things are going to get stricter and stricter. So that might be a potential solution for them in the future, maybe?
Yeah, there are these sintered graphite engine blocks that they use in diesels, and they have better acoustic properties. Someone could potentially use one of those in a gasoline engine and get an ultra-fast combustion chamber. Maybe better NVH mitigation, some more underhood insulation, or active engine mounts, you name it. It's possible. But
So-
I think they're just going to hybridize the power from now on. At some point, remember, it's a $1 billion development process, start to finish, to make a brand new engine that's emissions compliant. At some point, it's just much cheaper to slap a 200 horsepower e-machine, right? So a 200 horsepower motor, alternator, battery system in there, and get the performance that way. So sad as it may be, the engineer in me would really like to see perpetual continuing improvement in combustion engines, and sincerely hope it happens. But the value proposition of increasing power from hybridization seems to be hard to turn down for the OEMs.
I just find it funny, right? Like, for example, we keep seeing these stricter and stricter guidelines on ICEs, and then that's made leaps and bounds in like technology improvements. I almost wonder if like 20, 30 years from now or whatever, with hybrids and, electric vehicles, I wonder if there's going to be like restrictions placed on them. Like, it has to be this efficient. Like we were seeing with like fridges like 10 years ago, like now we have energy rated fridges or whatever it is. I almost wonder if we'll start seeing that with
Absolutely.
electric vehicles one day.
So, one of the things that pushed DI PFI systems and Generation 6 direct injection systems, so like the 350 bar, 5,000 PSI direct injection fuel systems.
Is that what defines a Generation 6 then?
Yes.
Okay.
Is that particulate matter emissions began to be measured and restricted. So particulate matter emissions is soot. It's small carbon particles from unburned fuel leaving the exhaust. Now we've got PM emissions from modern vehicles that are very, very small. But legislators creating these emissions regulations, they are not terribly interested in saying, guys, we've done it, cars are clean, let's pack up, I'm going to retire, right? Their job depends on them finding more stuff to legislate. So, you heard it here first, coming soon. It's actually really well known in the industry. They're going to legislate brake dust as a particulate matter emissions and tire dust. And that's really going to get the heavy cars, because the heavier the car, the more brake dust and the more tire dust it produces. So in a very roundabout way, you are going to start seeing these vehicles get legislated, but it's going to really impact their curb weight. So we may end up with cars that make less power, not because we're trying to limit power directly, but because in a push to try and limit brake dust and tire dust, we have to make the cars lighter, and that means making them less powerful. That's one possible scenario. I know the EPA is even trying to legislate particular better emissions from deep fryers. That's just how, I guess, desperate they are to find stuff to find.
Well, that's when you put it that way, right? Because again, if you want an electric car to be lighter, that means less batteries, which means less power, and that is crazy. It's going to come full circle in that regard if they make the push. Because the Hummer EV, we saw a trailer full of them on the way here.
Yeah.
I mean, each one's like 8,000 pounds or something.
My theory is GM built it to show the world that an EV does not have to be good for the environment. They're like,
Which a Hummer is very known for, right? Like they're not.
but that
ever
is
known.
just so bad.
Yeah.
Like it's just so bad. I don't think you could probably drive like an emissions deleted pickup truck and it would be better for the environment than a 10,000 pound, 1,000 horsepower, 200 kilowatt hour Hummer EV. Like it's obscene. Like I'm a car guy. I look at that and I'm like a little embarrassed that they made it. I'm like, no, that's not me.
Do you think we could have gotten here without the EPA with their boot on our neck? Or do you think OEs would have just been lazy and be like, this is working? Or do you think they would have still developed? So I feel like as they push, things get a little bit better, right? We come with better efficiencies, which makes cars can be a little bit faster, things like that. Do you think we would have still gotten here had they not been putting pressure?
Man, that's a really smart question. I don't think so.
No?
No, because at the end of the day, we do things either because there is financial gain to be had or because there's legislation to be complied to, right? OEMs probably would not have made cars safer if crash test standards didn't exist. I mean, maybe a couple things, right? Obviously, no OEM wants their customers to die in a car crash,
Right.
but no OEM wants multi-billion-dollar vehicle development programs for side impact airbags and specialized crumple zones and all that. It's the crash legislation really is what drove safety in vehicles. And similarly, I can't imagine a world in which OEMs would want to develop urea injection systems for diesels.
Oh, yeah, no.
There's no way. No way. Actually, I think if you told me in the 1990s that in 2010 I would have to be putting urea in my diesel truck. I don't have a diesel truck, by the way. I'm just hypothetically speaking, right? Urea, like pig's urine, in my diesel truck to drive anywhere regularly. I'll laugh. It's a ridiculous thought. Like, how? Like, where am I going to get this from? Like, gas stations are going to start storing pig's urine now? Like,
Yeah, in plastic jugs, which is totally environmentally
right.
safe.
And like, and if I run out, I can't drive anywhere. And you think people are going to buy those trucks? And here we are.
Yeah.
But as you pointed out, it's not all bad because with the push for lower emissions, the engines became more efficient. And as they became more efficient, they also made power more efficiently. And the improved engine controllers that were needed to make the engines clean also let the engines run much closer to the limit and safely. So it's not all bad. I'm glad you brought that perspective.
I believe that's kind of how the turbocharger was birthed, right? I mean, that was a way to make things more efficient, was running, let's force more air in by using exhaust gases as they're released.
I think it was a World War II technology.
Was it? Okay.
I think it was really designed to increase the performance of warplanes because...
that's right. Yeah.
Okay.
Yeah, like I shouldn't say modern, but yeah, like turbochargers the way we know them, that idea was, but like superchargers actually came along first.
Yes.
I think it was like a documentary or whatever. I watched it on YouTube. It was great. It was fantastic. It was like a 40-minute video. And it's like, it was designed to like speed up. I think it was the melting of like metal or something. I can't remember. It was like some sort of like...
I think the Roots blower was used in blast furnaces.
That's what blast furnace. There we go. Okay, we're caught up
and
now.
then I think that I forget the name of the company, something Auto Works, was a predecessor for Audi They slapped a roots blower on a race car, and it was legendary. It was unbeatable, right? Because it's supernatural. Like this thing is running more than 1 atmosphere pressure, so it can make power that no engine that size would ever be able to make. And then I think the war started soon after that development. So then they came up with the turbine-driven supercharger, which is a turbocharger.
Yeah, which basically allowed planes to like fly higher or whatever it was. Yeah, because they started to suffer after like I think it was like 16,000 feet or something. I don't know.
And that's something cool about turboplanes. Super off topic, but I like
pretty on brand.
airplanes. And so most turboplanes are turbo normalized. So what that means is they're not using the turbocharger to make more power. They're using the turbocharger to not lose power as they go up.
Okay.
So at 20,000 feet, air density is about 50% of what it is at sea level, which means that at 20,000 feet, you lose 50% of your horsepower. So if you can run 6.5 pounds of boost at 20,000 feet, you've got sea level power at 50% less drag. So the plane can go twice as fast. But you're not stressing the engine anymore because you're not trying to make more power than it was designed for. It's kind of interesting.
No, that makes complete sense.
Yeah.
That's,
Slight detour. Why GTRs, right? Because like again, you mentioned I think it was last year you tuned like 343 GTRs. I don't think we have that many in the Midwest. If we're maybe I don't know. That's a big swing. Why? I mean, that's got to be what 90% of what you tune probably.
Yeah, about that. I mean, it started off with I had a supercharged Corvette, and I got tired of losing races because
They look like GTRs from behind.
Well, the taillights maybe.
Yeah.
So I just got tired of not having traction. It was just big power rear wheel drive is so overrated. Sorry, Mr. Mustang guy.
yeah, no, that's fine. That's fine. I've been dreaming of something all-wheel drive, so we'll see.
Yeah, so when I sold the Corvette, I wanted an all-wheel drive sports car, and I couldn't afford a 911 turbo, or at least not a 911 turbo that I would want, right? And sure, some old enough one. And I had Subarus back in college, so I knew better than that.
Yeah.
I mean, no one goes from a Corvette to a Subaru. Sorry, Subaru guys.
Yeah.
Cool car, but so yeah, I was thinking about a couple different options. Audi was one of them, but not a ton of aftermarket support. And I like to modify cars. So the GTR was pretty much the highest performance all-wheel drive car that would fit my budget at the time. And I bought one, and I told myself I was going to keep it stock because I figure I couldn't afford to mod it and break it. And I pulled it off for almost a year until I was at SEMA and I was talking to Derek Catterfield. He used to be the main guy at Cobb. And I mentioned to him that I had a GTR, and he said, "Oh, well, what do you have done to it?" And I said, "Nothing." And he's like, "You must have the only stock GTR in the world." So he's like, "We got to change that." Gave me an Access port, gave me Access Tuner software. I tuned my car. I really enjoyed the experience of tuning it. Car was faster. A couple friends who had GTRs asked me to tune their cars, and then I tuned their cars, and from there it just snowballed into tuning more and more of them. And then at the same time, I started building up my GTRs. So I did bolt-ons, and then bolt-on Z85. I switched it to Accutech, upgraded the turbos, which gave me the performance to brake my third gear. So then I built the transmission, at which point you got to build the engine so you can really take full advantage of it.
Remember when it was stock about 30 seconds ago?
Yeah.
Yes. And next thing I know, I'm at TX2K 18 in my daily driver, made it to the semifinals. Ran 8.6 at 161, which back in 2018 was fast.
What class would that be?
I think it was 58 millimeter class.
Okay.
Yeah, so back then they had a class by turbo size.
I think they have a class now. What is it, 60 something?
So back then I think there was 58 and 66 or 68. But I mean, nowadays the 58 millimeter turbos are going 7s. So it's gotten so crazy. it would be impossible to have a daily driver car, maybe even qualify at this point. But back then, I had my car on snow tires, daily driver. I shipped it to Texas. I borrowed a set of slicks, put them on, launched the car for the first time in my life on slicks, went 9.0, made a couple tuning adjustments, 8.9, 8.7, 8.6, and then I just went 8.6 all weekend long. And it was great. And then brought it back home, put the snow tires on it, and kept daily driving. For me, that's the dream. Like, I think it's really cool if you can pull something off the trailer and go 6 seconds, right? But imagine how much enjoyment you're getting out of that car. I bet you're driving it for less than 1 minute a year. Whereas, like, my 8-second daily driver, I put 90,000 miles on it, and then I sold it for more than I paid for the car. Now, we won't talk about how much money I spent modifying it.
Yeah, we don't
But
count
you
that.
don't think
That's car
about
guy
that.
math. We don't ever do that.
No,
yeah.
it's
yes.
car guy math, exactly.
Yeah.
Yeah. So it was a good deal. It was a wonderful car. I loved it. I still love these cars.
There's something to be said about cars that you can just drive to the track and then go to Applebee's afterwards, which is exactly what we did. Like, with my friend's Nth Moto Viper, like, it was making 2,000 horsepower at the time, and went to the track, beat on it. I mean, we're talking back to back to back, like, ridiculous. I think he did like 9 passes that day, something, which is, by the way, unheard of. You know, but I think it was like a private event or something. I can't remember the specifics. And then we go get dinner afterwards, and then do hits at a speed limit.
Absolutely. So for me, that is the greatest achievement for a street car. And of course, I respect everyone's opinions. And I think if you can get a GTR to go 6 seconds in a quarter mile, that's spectacular. But realistically, right? If you want to drag race, you can buy a dragster that's going to do mid 3s in the quarter mile.
Yeah.
You can buy, if you want to go 7s, you can buy a methanol drag car for, God, what do those go for? $30,000, $40,000? And it's going to go 7.5 all year long. And getting a street car to go 7.5 means a ton of compromises, right?
Yep.
So in my mind, a street car made into a dragster is a lousy dragster and a lousy street car. Like, it doesn't drive great on the street. But there is a sweet spot for every car at which it's fast on the drag strip and still streetable and daily drivable. And for me, that's like the magical place to be, where you get the maximum possible enjoyment. You can get in the car, you can do a road rally, take your girlfriend, wife out for dinner, show your friends, drive it around, but it's still like fast on the track. And for me personally, it's important to not seek out those last tenths of a second at the racetrack at the compromise of what the car does on the street.
Yeah,
right?
you get an intercooler in your passenger seat or something.
Yeah, or like, let's say you gut the interior and like now it goes 0.2 seconds faster, but you have no interior. Like, is it worth it?
Is it worth it?
For some people, yes, but
God, that sounds like a conversation someone had with their wife. Is it worth it, really? This marriage for those extra 2/10?
Well, yeah, it gets to the point where now you remove the alternator. Like, every little bit starts to
There you
count,
go.
right? So now you only drive it, like you said, for 8 seconds at a time.
right, or you put like a 15-inch slick on the back, right?
Yeah.
So now it puts power down, but it drives like it's on marshmallows, and it just like won't corner to save its own life. Is it worth it? Like,
Yeah.
But that's the thing, is like when you see shops that do that utmost quality, like, again, my first experience in an Nth Moto Viper, you would not be able to tell it was stock. Or sorry, you wouldn't be able to tell it was modified outside of the fact that it's a little bit louder. The bead locks in the back, of course. And then the door bar. That was it. I mean,
Yeah.
you can't even see the roll cage in that car. It's just so well put together.
absolutely.
So it's like, but again, it goes back to your point. It's like there's a compromise, right? You're not going to run a 3-second quarter mile.
Right, but I think that's a really good example, and there are so many shops out there, right? And if you want to modify a car, like, there are probably thousands of shops all over the country that will modify that car for you, but there are very few places that can do work at that level. Or another really good shout out, T1 Racing.
Yeah.
I saw a T1 Racing GTR had a full roll cage that was built inside the interior. So they were able to run the pipes underneath the A pillar, you couldn't even see the car was caged. Just the attention to detail and then how far they went and like taking the car apart to get that, to have a car that now can be compliant with an HRA rules, right, and run on the track and have the safety. And I'm sure I didn't get to drive the car, but I'm sure the drivability is something they pay a lot of attention to. So I am sure these are not the cheapest shops in the country, but when you look at the work that comes out of there, you can understand why they charge what they do. And it's not comparable to something that like your local mechanic down the street can do by just putting a bigger blower on your car and like leaving it at that.
Speaking of cost, where do you guys fall? Like as Nostrum, where does that fall in the race to the bottom? Like where do you guys stack up against the competition? Are you the most expensive on the market? If so, why? What's the value proposition there?
So we are well aware of what our competition costs in places where there is competition. There are a few products for which no one else makes an equivalent product. Just off the top of my head, I think the Subaru high-pressure fuel pump, we're the only ones that make one right now. So it can cost whatever we want it to cost, and obviously it's priced according to what the market can bear. And we think it's very fair and it sells really well. Actually, that was our best-selling product when it came out. We sold our entire inventory in 24 hours when we launched it. It was a really cool product launch.
How much inventory did you have?
I think it was like 100 pumps in 24 hours. But still, it's pretty
We
good
didn't talk
launch.
a lot about pumps today. We talked mostly about the injectors, but like you guys probably kick out a ton of pumps too then.
Oh, yeah. Well, because on DI systems, if you don't have enough pump capacity, the injectors...
That's true.
Right? They're irrelevant. So... but yeah, in products where there is competition, we're priced in line with our competition, and we're not cheaper, we're not necessarily more expensive, comparable, but with a lifetime warranty and with the best processes, the best data, the best quality product. So we try to win out on quality. We intentionally don't get much into the PFI side of things. We have a few PFI products which are all application specific. And the reason is a lot of PFI nowadays has just gone into the race to the bottom. Like the cheap stuff is from China, and it is just you can't make it for cheap enough to compete with that.
Is there an application where, is it basically if I'm buying injectors or a pump, is that usually always a package deal, or is upgrading one over the other okay at a certain level?
So if we're talking about direct injection specifically, it's simpler than you might think.
Okay.
So the high pressure fuel pump in a direct injection engine is a constant torque device. So constant horsepower device, my bad. Every revolution that pump moves a fixed amount of fuel, takes fuel to make power. So essentially it can just make a flat amount of power. The fuel injector usually runs out at high RPM where the injection window is getting shorter and shorter. So for a lot of vehicles, they will run out of pump much before they run out of injector.
Okay.
For Infiniti VR30, so Q50, Q60, 400Z, there is no point in upgrading injectors if you have a factory turbo. But if you upgrade the pump, you can make a lot more power. So for that particular car, it makes sense to do the pump before the injectors.
Okay.
For some cars, they have enough pump capacity, but they need more injectors. I think BMW S55, it has a dual pump system. So that one has enough pump capacity, runs out of injectors. You'd want to do the injectors first if you had a bolt-on E85 car. So it's really application specific.
Okay.
I've heard you guys bring up the VR30 a handful of times today as we were kind of getting ready to do the episode. What is it about that platform that's so attractive to you?
So for me, it's near and dear
Okay.
because I got to experience the full gamut of product development in that car. We leased one for $250 a month as a development vehicle. we developed the first ever high pressure fuel pump upgrade for it, which then allowed us to tune it on E85, which meant that we had the first ever E85 VR30, made 500 wheel. We entered into the Battle Creek Speed Fest, which is a local airport half-mile event, and cleaned up. It was so much fun. There was a Ferrari 458 Italia that lined up next to us, and we just put buses on it, and like no one could understand that it was the most bare bones basic. It had the really ugly factory entry level wheels, but it was fast. And then afterwards, we developed the injectors for it. And then AMS made a turbo kit for the car. So we put a turbo on it. And that car ended up making about 650, 700 wheel horsepower, which back then was quite a bit for the platform. So it was a really good experience. The other reason is also it's one of our best selling products. So we move a ton of inventory for VR30 through AMS. They have exclusivity on the platform, and it's just it's one of those cars that has a really good balance between what it costs and how much performance you can get out of it. So it's a good tuner car.
Here's one thing that just kind of came to mind. So when it comes to choosing a market to make things for, I mean, are you looking at what's coming out now and preparing for down the line? Because not all cars go through the development process right out the gate, right? Like we're waiting for ECUs to get unlocked and whatever. So you're thinking about stuff 2, 3, 4 years down the line. So do you ever kind of look back, like what came out 10 years ago and is starting to catch traction for the modding or the aftermarket side? Or is it strictly focused on what's coming out today?
We do both. So we do product development one of 3 different ways. So one of them is we have a very close relationship to Ecutech and Cobb, HP Tuners, EFI Live, Hondata, MHD, Boot Mode. So when they're about to launch or when they're launching calibration support for a new vehicle, we pay attention and we consider supporting that vehicle with a fuel system, because the moment you can calibrate it, that means that you can make more power and potentially you can use a bigger fuel system. The other way is we look at the market, and that can be looking forward or backwards. So we could look backwards and say, wow, it looks like Ford has really made a lot of 3.5 liter EcoBoosts. I wonder, now that the cars with these engines are getting older and they're getting cheaper, enthusiasts might be buying them and they're modifying them and there's calibration support, so maybe we can make a fuel system there. Or we can look forward and see, okay, well, GM just launched the new Corvette Z06. It's got an LT5. People are probably going to be turbocharging that. What fuel systems in that can we make an upgrade so that as the boosting systems start to hit the market, we've got the fueling solution for it. Or the third one is companies just come to us, like Hondata came to us and they wanted fuel injectors for the Type R, Civic Type R, and we did the development for them for that.
So I'm curious, right? Who's a counterpart to you, right? Because like you're obviously in this fuel injection space. Do you pay attention to people that are like, in the aftermarket turbo space and any like stuff like that?
Yeah, we're very involved in the aftermarket. We've been going to SEMA for several years. We go to PRI, so we know all the big shops. We know the companies that make the supercharger kits and the turbo kits, and we talk to everyone. And I always make it a point to talk to these people and say, so what do you guys think is the next big thing? Or what are you working on next? Or what do you think might benefit from fuel system support? And sometimes we get some really good insights. So it's always a factor in how we plan future products.
Speaking of, since we've been on direct injection topic quite a bit, but can you tell me why a car would have both port and direct injection?
That's a good question. And a lot of people think that the reason why we went from PFI to then direct injection to now direct injection plus PFI is because of trying to clean the intake valves or issues with deposits on the intake valves. But the actual reason is 100% entirely because of emissions legislation. So what happened was direct injected cars are very clean. They have very low emissions. They had no issues meeting all of the Euro 5 and the EPA legislations for pollutants, but they did have an issue with particulate matter emissions, so PM or soot. What happens is with direct injected engines, some of the fuel spray is still in the form of droplets as the combustion begins. Those liquid droplets, they char as they burn and they form these really small carbon particles. Once PM started being measured and limited by Euro 6 emissions regulations, OEMs had to come up with solutions for eliminating the particulate matter emissions. And 3 different solutions arose. So one of them are the Generation 6 direct injection engines, like the BMW B58 and the Supra or the S58 or all the newer Mercedes. They're running 5,000 PSI, 350 bar, higher injection pressures, so you get better atomization, smaller fuel droplets, less PM. The other solution was gasoline particulate filters, GPFs, very similar to diesel DPFs. They soak up all of the carbon soot in a ceramic matrix and then they burn it off. And then the third solution was the PFI DI. So what these engines are doing is they're using port fuel injection in operating regions of the engine map where soot is likely to be generated. And they're doing that to minimize PM production for emissions reasons. And then they run DI in high load operating regions where the engine is knock prone. Because the primary benefit of direct injection is in raising knock threshold to allow you to run higher compression ratios, more ignition timing, more boost without knock.
Okay. Is there a limitation to direct injection horsepower-wise? Because I also know in the Coyote platform, a lot of times the guys will delete the DI and just go with port injection. Is there a reason why they would do that, or that? And that could be specific to the Coyote platform. Does DI only take you so far, or should it take you further than port?
Oh man, I'm having a hard time being polite here. I want to make a comment about Coyote owners and deleting
Hey,
DI.
you go for it, man. I'm a glutton for punishment. People.
All right,
I
I will put this as politely as I can.
Sure.
I believe that it comes from perhaps a lack of technical understanding of why the DI is there in the first place.
Okay.
But okay, so let's answer this in a way that maybe helps people make a good decision, right?
Mm-hmm.
I think if you're thinking of deleting DI, you have to start with the question, well, why was this engine direct injected in the first place? Because direct injection fuel systems are very expensive. You're talking about a 3,000 to 5,000 PSI fuel pump. You're talking about fuel injectors that go directly into the combustion chamber. Multiple times the cost of PFI. And OEMs don't do anything unless it makes financial sense. So for them to have spent all the time putting that direct injection system in there, surely there was a reason, right? And the reason is, with direct fuel injection, because you're evaporating all of the fuel inside the combustion chamber, you end up with much lower end of compression temperatures. So the primary benefit of direct injection is lower temperatures inside the combustion chamber. What that lower temperature does is it allows you to run a higher compression ratio and or more boost without knock. If you look at every single engine that went from PFI to DI, Subaru EJ to Subaru FA, the GM LS to the GM LT, the VQ to the VR, all of these engines gained at least one compression ratio point. And the first thing you find when you delete the DI is that now it behaves like a high compression ratio engine running PFI, meaning it wants to knock. So there's a really big loss in knock protection or knock resistance from doing that. And sure, if you're running E85 or if you're running race gas, that's probably not a factor. But it certainly is one of the disadvantages, because that is the reason why the system is there in the first place. Now, why are people doing it? Other than my pet theory that it's because the people doing this just don't know any better. DI systems are limited. It's very difficult to get extremely large amounts of fuel into the combustion chamber in the very short time duration that you have for a DI injector. Because you can't start injecting until the piston has already started to come down during the intake. Otherwise, you're just injecting on the piston, right? And you can't keep injecting when the piston has come up again and the spark plug is about to fire. Otherwise, you're just wetting your spark plug, you're wetting the piston. So your injection window in a direct injected engine is very short. It's less than 40% duty cycle. So you're losing a lot of time, which means that the fuel injector is limited in how much power you can make. We've done 1,500 horsepower with Ligenfelter on a DI-only LT4. That is about the power limit. If you're trying to make more than that, you will most likely have to bring in some of the fuel from port. But some of the fuel, there's really no reason to try and bring 100% of it from PFI, and there are a lot of reasons not to.
Okay. So would you kind of put it in a class? So back when I started collecting Fox bodies and doing stuff like that, a lot of guys would take the engines, they'd swap them, and they'd go back to carbureted.
Oh my God.
Right, which is because it was a lot of times it was older gentlemen, people like that. It was a technology they understood.
Oh.
Would you say that it could be a situation in that, like, where the people doing the cars, tuning the cars, doing that kind of stuff, they just don't understand that technology yet?
Yeah, and I mean...
Or we're waiting for somebody to go ahead and develop us a high-pressure fuel
right.
pump. And
let's be fair, right? If I'm building some rat rod in my garage... to go like do burnouts with my friends, like, who cares? Slap a carburetor on it. Like, you know, you can do whatever you want. It's your home project.
Right.
But if we're racing, I think racing is always a good example, because it brings out the best in everyone, right? Like, if we're racing and you've got a carbureted car and I've got multi-point electronic fuel injection, and we both have the same size engine, you're going to have a really hard time beating me, because you've got much better controls, much tighter air-fuel ratio control. There's a lot more you can do with electronic fuel injection and electronically controlled engines. Similarly, if you've got a PFI-only engine and I've got PFI DI, and these are both street cars running pump gas, you're going to be running into knock much sooner than I am. So I think I understand that it's technically more challenging and the fuel system is more expensive, but the payoff for using the cutting edge technology that Ford has already put in there for you is well worthwhile.
right.
And the knowledge is out there. I mean, this is not the early 2000s when DI was just new to the market. I think there's enough information out there that people can figure out how these systems work and work with them.
And I don't know what that limit's at, and that I know that there's some people that do delete that, and I don't know at what power level or where it gets. I haven't.
I remember when the Helion turbo kit was being developed for the Mustang, the first DI Mustang. They were deleting the DI system. I don't remember what their reasoning was for that, but I remember knock was a really big concern, big issue they were running into, and yeah, I'm not sure why they would get rid of it. Beats me.
Yeah, I don't.
Just don't
Nobody
do it.
likes knock.
Just don't do it.
Yeah.
Well, as we start to wind down here, because we're closing in on that 2-hour mark, which it's been a great conversation so far. Is there anything that we kind of haven't touched on that we said we would touch on from your side?
Oh man, I wasn't prepared for that. Well,
I think we mostly have covered all of it, or not. I shouldn't
so.
say all of it. There's a lot that goes into this, quite a lot. Whether it's the Nostrum side, because again, we talked a little bit about the development of stuff. Again, a lot of research goes into this. I mean, you guys were showing us some stuff, on the computers, and we're talking about things that take, is it photos? Not really photos, at like 1 million frames a second or something like that.
High-speed imaging.
Yeah, high-speed imaging.
Yeah.
Like, when you look at it on the computer, you're just seeing how things come out and evolve. Like, that is ridiculous. I mean, not everybody's doing stuff like that, right?
I mean, it's like going to a good mechanic's shop, and the higher quality tools you have, the better job you can do, right?
Mm-hmm.
So we believe in using OEM methods and OEM tools to produce OEM quality products. And everything that we do here reflects on that.
I got a real quick one for you, and this might be a really stupid question. Again, I have not looked into it, so if anybody's out there listening, you're like, why would that idiot ask that question? I've always meant to Google it, but I never have. Can you tell me why sometimes I see them, they're rated at pounds, and sometimes this is probably, maybe this is just a port injection issue, but sometimes I say these are 1,000 cc, these are 1,300 cc's, and I also see these are 75-pound, 47-pound injectors. Why would there be two different measurements for that? Or
I think it's mostly like a US versus metric system thing. Yeah, because it's a little bit like rating torque in foot-pounds or Newton meters. You can convert back and forth. Now, it's important, though, that as you convert back and forth, you take into account the fact that gasoline density is not the same as water. I've actually seen our competition take the flow rate in pounds per hour, convert it into grams, and then convert that into cc's as though the density was 1-to-1, which would be like the flow rate in water, but gasoline is about 0.75 grams per cc. But yeah, they're exchangeable.
okay. Does E85 and gasoline have the same viscosity?
E85 is a little bit less viscous. It has a
Okay.
little less lubricity too, which is part of why it's harder on components.
Okay. There was another one I had in there, like a rapid fire one, but I don't remember it now.
I know you're on a roll there.
Yeah, I know. Yeah, I got
It's
nothing.
gonna make you struggle on that one. No,
Yeah,
it's
that's
okay. It has been an incredibly long day. Again, this is an awesome tour to check all this stuff out. I mean, I learned more about fuel than I ever cared to. But why is it such high pressure, right? Like, and again, sounds like a simple question, but like we're talking about, what was it, 350 bar? That's about 5,000 psi.
5,000.
I don't think there's a ton that you have to overcome forces-wise within the cylinder unless you're trying to do it for a particular reason. Why is it that it's such a high pressure when you're shooting it all in there?
It's time. So at 7,000 RPM, you've got something like 12 milliseconds to have the intake port open, inject your fuel in there, atomize the fuel, mix it with the air, evaporate it, compress it, ignite it, and burn it. And the only way you can get the fuel in there fast enough is by having very, very high flow rates. And the only way you can get high flow rates with good atomization is by having very high pressures.
Mm-hmm.
So, and then with diesels, obviously, even higher pressures. Typical modern diesel runs 30,000 psi.
So much so that it has to be hydraulically ran. That's one of the reasons that diesels need 15 quarts of oil, because they're using half of it to run the injection system.
Diesel pumps use like 15 horsepower too. So
Yeah.
it's
I remembered what I was going to ask. So you said this was all birthed from developing a water injection system. Can you tell me why you were developing a water injection system and what it was used for?
So there was some legislation coming up that was going to essentially mandate Lambda 1 operation under all foreseeable conditions. So what that means is right now, when you're running your car at full power, maximum load, it uses some excess fuel to lower the combustion temperature. And that used to be called power enrichment. So power enrichment was legislated out by name. So you can no longer enrich to increase horsepower in the OEM world.
Mm-hmm.
But you can enrich for component protection. So a really good example of that is if you get a Ford Raptor and you put it on the dyno and you do a third gear pull, it will finish the third gear pull at Lambda 1. It's just running stoichiometric the whole time. If you do a fourth gear pull, it takes longer to finish the dyno run, and at some point it actually goes rich. The reason why the car is going rich is because there's a lot of heat being generated when you're running Lambda 1, and adding excess fuel increases the heat capacity of your mixture, but doesn't increase the amount of energy being released, because you only have so much air to burn the fuel with.
Yep.
So all the extra fuel does, it just cools down combustion. So the rumor was that Euro 6 and RDE, RDE is real driving emissions, that the way they were going to test emissions was going to make it such that you could never do that again. So under that premise, you would essentially lose a lot of power from existing engines. Or you'd either have to make the engines physically larger to get the same power, you have to find some other way to get that power that you're losing by not being able to enrich anymore. And we were working with an OEM on a project that was going to use water injection to do what the fuel enrichment was doing for combustion temperature control.
Okay, because I'm thinking, like, what world would you want to spray water into your engine?
It's pure octane. Think about it.
Yeah.
Right? So water has an infinite octane rating because it doesn't burn. It just suppresses knock.
Mm-hmm.
There are challenges and limitations, but we had a project, I think it's been published already, the High BMEP project, 600 horsepower, 600 foot-pound torque, 4-cylinder, running 85 octane. And it was all done with direct water injection. So we mapped out where the engine would knock, and we added water to suppress the knock, and we're able to operate it as though it was running race gas, but with regular pump.
Really?
Yeah.
So is that something we may still see down the road, or?
I think, as with a lot of other innovation in this space, it will depend on where legislation goes.
Okay.
So,
But I imagine that would be tricky, especially when we go down the hybridization of stuff. I was watching the Engineering Explained video the other day, talking about how, like, it's getting water out of the systems getting more difficult because engines can't get to operating temperatures. I can't imagine that. I'd imagine that have some sort of effect on it too, right?
we were actually recapturing a lot of the water from the exhaust.
Oh, okay.
Yeah. Otherwise, you'd have to have a water tank that you keep refilling.
Right, okay.
Yeah. So every pound of gasoline that you burn produces about 1.4 pounds of water.
Oh, wow, okay.
And then when you add additional water to that, now you've got a really water-rich exhaust. And if you cool the exhaust out and run it through a cyclonic separator, you can pull the liquid water back out, filter it, and put it back in the engine.
Which, by the way, probably doesn't work well in Michigan in January, or
No, but
do you add methanol
but
to it?
do you
then?
need to make 100% full rated power in Michigan in January?
Yeah, I guess
Right?
not. Yeah.
I mean, there may be situations where you do, but for a sports car, certainly not.
Yeah. Okay.
All right, and we're back. So one of the things I wanted to ask you, and Dan did point out that may have touched on it a handful of times during the episode, but like one of the things you showed us was like the mapping, right? I think that's plume mapping. Is that the proper terminology, or?
For the fuel injector mass distribution, yeah.
Yeah. Yep.
Mapping.
So, is there like a particular shape or like a certain way that you want it to go into an engine? Is there like a generalized way, or does it get specific by application? And if
It
so, what
is
applications?
Super application specific.
Okay.
Yeah, and every engine design is different. So if you have a centrally mounted direct injector, as is found in a lot of BMWs and Mercedes-Benz, they tend to have a more symmetrical spray plume, whereas a side-mounted DI injector is going to have more of a downward-facing plume. But even within that, they alter the plume shape for improvements in cold start or idle stability or minimizing particulate matter emissions. It's a very complex topic, and what we normally do is we try to mimic the OEM spray pattern because the OEM has already spent a lot of time optimizing it.
Right. Well, especially if you're talking about like the top of pistons and how it all
Yes.
works. So then when you're like a top tier shop, like, you know, your AMSs, your Nth Motos or whoever, right? Maybe more like AMS because they distribute to a larger market. When you're making like aftermarket like pistons or whatever, are these things that you have to take in consideration as well as how is it going to work with an injector pairing, or is that getting a little bit too into the nitty gritty?
Ideally, yes, but we've also seen situations where the piston topology is eliminated on some high compression ratio pistons, and there is some loss of cold start quality, but for the majority of customers, that is an acceptable trade-off for a stronger piston. I think it really depends on the intended market. A lot of times, by the time you're building the engine, you've got a lofty enough power goal where you're willing to live with a little bit of compromise to things like cold start.
Is there an aspect of developing an injector that is harder than one or the other? Would it ranging from wide open throttle to cold start? Is there an in between one that's harder to nail than the other?
By far, the hardest aspect of developing a direct fuel injector or a port fuel injector is in the short pulse duration behavior.
Okay.
So it's really easy. You could probably just have a tube going into the engine, pouring fuel in there to meet your maximum power fueling requirements. But getting it to idle properly on gasoline when the engine is warmed up and you've got a really, really small fuel quantity requirement is by far the hardest part.
Okay. So just after the cold start, the part where it just sits there and idle is the hard one.
Warm idle on gasoline is the hardest part.
Okay.
What about cold starts and just that? Like, for example, my GTI is DI, and I keep it outside, and it's negative 20 degrees sometimes when I've started my car negative 50. But is that pretty difficult to engineer for as well then?
Yeah, particularly if you have a high flow rate injector and the OEM strategy involves multi-pulse injection. If you try to break up the injection duration into smaller durations on a big injector, you can ask the injector to deliver a fuel quantity that it can't. It's just not controllable at that short of a pulse duration. So we have a lot of tricks that we use there. Sometimes we're able to disable multi-pulse injector when we get some really high quality cold starts. Sometimes we intentionally lower the fuel pressure on cold start so we can lower the flow rate a little bit, get a longer injection duration. A lot of that is trial and error. And this dyno cell that we're sitting in is climate controlled, so even in the summer, we're able to cold soak a vehicle in here for 24 hours and then do some cold start work and start developing some of those strategies.
Cold soak, that's the first time I've heard of that.
Yeah.
That's pretty cool. So then what's that all managed by? Does that kind of all go back to the ECU then? Like when you're doing like multi-pulse and all that stuff then?
It all comes back to the ECU, but specifically what control strategy the ECU uses and how we as calibrators can best work with it. So a lot of times maintaining the ECU strategy is the best approach. They've put a lot of thought into it. Sometimes because of the changes that we've made to the fuel system, we have to make changes to the OEM approach, and that all goes back to development work and just trial and error, getting a car and working on it.
Is there an OE that's harder to work, like harder than most?
You Ford people.
Sure.
And you don't have to answer that if you don't want to call out.
They all have their quirks, right?
Right.
So Dodge uses a neural network to do their ignition timing. So HP Tuners now has a service where they will retrain your neural network if you change camshafts. Porsche, I think the last one that I tuned had like 15 ignition timing tables with no indication of which one was being used and why and where. So you're like, I think I could use a little more ignition timing here. And then you got 15 tables to change. And like, what do? You change all 15, and now maybe one of those tables is like the fallback, like high knock, low octane timing table, and you just put timing on that, and you don't know because you're not operating on that table. So,
and there's no way to tell which one's which? Or
okay, so certainly at the OEM level, there is, right? Like, I'm not saying that they're doing this in the dark, but
Imagine.
at our level in the aftermarket, there doesn't seem to be a flag where that has been made available in the software that I use for tuning Porsches, where I can see which one it's running. Cobb was kind enough to make this like global adder that says, well, whatever timing table you happen to be in, take this one and add to it, which is a really quick and dirty way to get more timing done. But that one's a pain. BMW has at least 50 tables just to control the exhaust sound. It's asinine. So if like the customer says, well, can you, I don't know, make my exhaust valves open at like a lower RPM or something? It sounds like a really simple request. And in my mind, there should be a table that's called exhaust flap position versus RPM. But there isn't. There's like 50 and they have German names. So so BMW is really rough. I would say those are like the top three toughest cars to tune.
Because I know information is information, but how that information is deciphered, it can be however you want to do it as an OE, right?
Yeah.
Being German doesn't help either.
Yeah.
Well, and what's important to remember is when we're tuning a factory engine on a factory ECM with like HP tuners or Cobb or Accutech, what you're looking at is just what they have made available to you to modify. It's not the whole ECM. So the whole ECM probably has 1 million lines of code and it's got thousands of tables, and maybe they take 150 tables and they make those available to you because they deem those to be the ones important for your goals of increasing performance. But once in a while we do run into situations where the thing we need to change has not been uncovered by the company that makes the tuning software. And then for us in particular, working in the aftermarket fuel systems, it's really useful to be able to communicate that with the company and then have them add some of those controls for us.
Okay.
So then at what point do you say F it and get an aftermarket ECU like a Haltech or a Motec or whatever?
Ooh, that's a good question because it's a double-edged sword.
Yep.
So if we take the factory ECM out of this GTR and we slap a Motec in there, for example, right? We gain a lot more control over all of the functions that the ECM has. The traction control works much better. It's much more adaptable. Launch control works much better. So we've got some real advantages there. But a vehicle will fail any emissions testing of any sort forever. So it's highly illegal for a factory vehicle. Sorry, for a street-driven vehicle. Also, the other thing is you have a lot of control, which means there are many different ways in which it can be worse than factory too, like your cold start or your idle or your low-speed drivability. These are things that the factory has teams of engineers working for years. I dated a girl that worked at General Motors, and she was one of their calibrators, and they had these vehicle development programs where they would ship cars out to Arizona. They would do full hot weather calibration on them, and then they would ship them to Colorado, full high altitude calibration, and then they would send them up to the UP and then winter tests, and they would do that 2 years in a row. And then when vehicle development was delayed, they would ship the cars out to a mountain in New Zealand, and they would do winter tests there while they were doing hot weather tests in Arizona. And this is all just for making sure that vehicle drivability is good under all foreseeable conditions. Well, when you slap a Haltech on your car, you're not going to do that. No one's going to do that. So the moment you drive it into high altitude or very cold weather or very hot weather, you're going to find out everything that wasn't done in the calibration. So they tend to be a little quirkier. Generally speaking, I would say it's a fantastic solution for a race car. it's perhaps not necessary on most street cars.
Well, you can only account for so many things. Like if you're running a small shop of 4, 5, 6, or let's see. I mean, even 20 guys is a small shop. We're talking that versus an OEM that has thousands of employees.
Yeah.
And dedicated, like you said, teams of 20 to 30 to this one minute detail.
That's it.
So, I mean, I think it's nothing short of a miracle to see some of these 1,000 horsepower aftermarket cars that are daily driven or street driven.
Oh, and they do really well. And of course, that there is a point in which you just modify the car so far away from factory spec that the fact the OEM spent $1 million doing just cold start is irrelevant because it no longer applies to what you have under the hood. But generally speaking, I would say you don't want to do an aftermarket ECM unless your build really demands it. You're really at the extreme end of what the platform can do.
And you've mentioned that you've done, what, up to 1,200 or 1,500 horse on stock GTR ECMs?
I've personally done north of 1,500, and I think the record is much more than that, 1,900 maybe. It's in that ballpark.
So what's the limiting factor then? Or what's something you're missing out on that forces that upgrade, I suppose?
It's a good question. It used to be that when you started really pushing these cars into extreme power numbers, they got a little bit unpredictable, meaning some of the behavior wouldn't match what you expected it to. Like it did things it wasn't supposed to because you're just running off the maps in the ECM. That doesn't seem to happen anymore. I think the software is really well polished. I think one of the reasons why you really would want to have like a Motec or a Cyvex at the 1900 wheel horsepower level is because traction control with a factory CM is not going to be adequate anymore. So that would be a big reason for me.
And that's kind of like where, especially with all-wheel drive cars, you start thinking more about using GPS or whatever in that instance.
Yeah.
Is that all that there? So this is a space that I'm trying to learn more about, and I will as this little journey continues. But is that what other options are there besides doing like GPS for traction management at that level?
Well, so the GTR is very heavily rear biased.
Right.
On a Nissan GTR, you'll typically lose traction from the rear tires well before you can overwhelm the front tires. So you can do traction control the conventional way where you're dividing the rear wheel speed by the front wheel speed. That gives you a wheel slip, and then you've got a wheel slip versus vehicle speed driving torque reduction, and that cuts power as the car begins to lose traction. You're good. If you have a locked center differential, or if you have a very stout all-wheel drive system where they're really both spinning at the same time, you could have a wheel slip value of 0 even though all 4 tires are just going up in smoke.
Yeah.
At that point, you really do need GPS. And then what you're doing there is you have a GPS vehicle speed versus a wheel speed predicted vehicle speed. And you can say, well, according to my tire rotational speed, I should be going 100 miles an hour. My GPS is telling me I'm doing 40, so I am definitely roasting the tires. And then it goes into the strategies. The thing I always wonder about is I tune a lot of cars in Norway. I've probably tuned every GTR in Norway. Maybe not. I've tuned every GTR I know of in Norway. And those guys, they're really nuts. They race in tunnels. Like, it's the thing there. I haven't been to Norway yet. I really want to. But every video I've ever seen from street racing in Norway, they're inside huge tunnels. And these are like massive highways cutting through mountains. And the cool thing is the weather there tends to be cold most of the year, and it rains a lot, and you don't get a ton of good driving days. But inside the tunnels, it's dry, so they can put power down. But what is your GPS-based traction control going to do when you're doing a 1,500 horsepower pull inside a tunnel? Right? It's not going to report any speed. So I don't know that there is a way around that. I mean, obviously, your vehicles and your phone's GPS are using accelerometers to at least know if you're still moving, right? So it's able to understand when you go into a tunnel that you didn't go into a tunnel and stop your car, that you're like going through the tunnel. I wonder if there is a solution for traction control that uses that with fine enough resolution to work. I don't know if there is or isn't. I've never had the need to look into that, but yeah, it's an interesting thought.
Should we pop the usual 3 then?
Yeah.
I just looked at the clock. We've been here for 6 hours. It's basically a full workday we've been here.
Yeah.
Almost.
Oh, damn.
All I know is that I need to go to Norway now for sure because I've always
That
wanted
sounds
to.
awesome.
It's
Tunnel
I need to
racing.
be part of the street scene out there. So
The tunnel scene.
yeah, see this is the tunnel scene. All right. So at the end of every episode, we like to ask our guest to pick 3 cars. You can have a track car, a show car, and a daily driver. You have an unlimited budget. You can swap whatever you want. What are you picking?
All right. Track car. I think McLaren 765 LT. I know everyone's like Porsche GT3 RS.
Yeah.
I think it's the most overrated car ever made. Like 300 grand for a naturally aspirated 6-cylinder. No thanks. So
Okay, what draws you to the 765, the most unreliable? No, I'm kidding.
yes,
I'm kidding.
that is certainly a concern. Absolutely.
Unlimited budget, though.
Right. Set unlimited budget. They're so light. The curb weight on McLarens is unreal. I mean, they're barely over 3,000 pounds in a modern car. I think it's spectacular.
Well, especially when the windshield's like 1/3 the thickness that it cracks or whatever. Did you see that?
Oh, yeah.
The 720s or the 765s, the windshields were so thin that they were like starting to warranty them for cracking or whatever. Really.
Yeah, like the roof glass breaks too. But okay, so in my mind, that's the ultimate track car.
Sure.
Show car, have to be a resto mod. So when I was a Corvette guy, I was at Corvettes at Carlisle, and there was a C2 Stingray with full ZR1 running gear, and it was gorgeous, and it had the perfect classic look with the side pipes and everything, but the modern running gear. I think that would be my show car.
And it was at Carlisle, you said?
Corvettes at Carlisle.
Corvettes at Carlisle.
Yeah.
Okay.
Pretty
What color
cool
was the
show.
car?
It was red.
Red. Okay.
Apparently, it was George Cook's car. So,
So it
from
had
Cook's headers.
like the C6 ZR1 drivetrain in there?
Yeah.
Okay.
Yeah, it was really cool.
In a C2, that must have...
Daily
that thing
driver.
moved.
All right.
Really?
So I have a friend that lives in Colorado, and we drive up the mountains a couple times a year for snowboarding. We've had this conversation many times. We both agree that if money were no object, the ultimate daily driver car, the highest performance that you could take everywhere, if money was no object, Bugatti Chiron. I think if money didn't matter, you could drive that summer and winter. You could probably slap on a snow tire on it. Ground clearance might be an issue, but money is no budget. I'll just buy a new front lip when I find something that's taller than the front lip. And it's a Volkswagen, right? So it's going to be reliable and quiet and comfortable. That's it.
You gonna lift it or anything for anytime you go out to Colorado?
I mean, I think I'm just going to hit stuff with it and then bring it to the shop and get it fixed.
Well, if you get stuck in snow, you kind of want those off-road tires and stuff.
That is true. I hadn't thought of that. You could high center it, huh?
Yeah, so maybe throw a lift kit on a Chiron. Is that what you're telling me?
Yes. Lifted Chiron daily driver.
The comment section just exploded. All right. Well, sweet. On that note, is there anybody that you would like to shout out or anything that we just haven't covered, or anybody that you just kind of want to give some attributions to?
Well, first of all, I'd like to thank both of you guys for coming all the way here. It's very flattering that you guys came here to talk to me, so thank you so very much.
I'm super happy I reached out to you. You're the first person I reached out to for this trip.
Oh, that's awesome.
Just because I can't even remember Facebook stuff or whatever. I'm telling you, man, you just got to... You see a car and a profile picture, you add it.
You guys have
I'm
been
like
very
that, too.
hospitable as well. We really appreciate everything.
Well, thank you again for coming. And, of
Yeah.
course, I'd like to thank Frank and the rest of the Nostrum team for...
I'm mad at Frank for not being in here. He's super cool, too.
He's awesome.
Yeah,
Yes.
we'll be back here. We're going to get him on
He
next
was
time.
up at the glass making faces earlier. I don't know if you saw that.
He was making faces. I'll look at the camera later, though.
Yeah, and also, since we've been talking so much about calibration, I think it's really important to recognize everyone at Ecutech, at HP Tuners, Cobb, Boot Mode, MHD, EFI Live, Hondata, everyone that makes the software that allows us to pursue our passion in the aftermarket. This can't be emphasized enough, because if you can't modify a car, well, if you can't tune a car, you can't modify it. And if you can't modify a car, what's the point? So,
Yeah.
I love it. What a perfect way to end it. On that note, guys, thank you very much for tuning in. Sam, where can we find you?
oh. So my tuning page is Power Labs Tuning on Facebook. And you can also message me, Sam Barros, on Facebook. I probably won't add you, but you can message me.
Thank you very much for making this happen. This has been awesome. Dan, thanks for existing, and we'll see y'all next time.
Thank you.